Okay, is it working? Right. Hello everybody. I'm going to talk about my compile time multitype pool allocator, which is an allocator that uses fixed types for a pool to reduce fragmentation and give some guarantees. So the requirements of the allocator that I have is that you have an unknown amount of elements, so you can allocate some amount of elements. You can allocate one of multiple sizes, and there should be some guarantees about in what time the allocations are made. So right now there are basically two main strategies. You can either use a heap, which has a potentially unbounded time, and it suffers a lot from fragmentation, so it's not optimal. And you can also use a pool, which mainly is one size only, and if you do want to use multiple sizes, then you would have to create multiple pools, which actually creates a lot of fragmentation in itself because you cannot reuse the same memory twice. So my solution here is by creating a pool type where you put all your types in that you want. Then it does some calculations, you get a pool type out, and then you get better fragmentation and memory usage. And also you can get compile time guarantees about the performance of that pool. So this is the goals for the code. It should be modular, expensive, clean, all good coding practices, basically. Right. So this is how you create a pool type. You see here, you call a basic allocator, then the magic multitype pool type, you put all your allocator types in it, and then some policies to give directions to the algorithm. And at the end, you actually create the allocator objects either on the stack or on the heap or somewhere else in global object space. Library is used, it's MPL. I mean, I wrote it partly, so I'm very familiar with it, and it's a lot of metaframing. So, yeah, MPL is pretty necessary here. So the design of a multitype pool is basically in three parts. You have your allocators, and then you have the combinations of allocators to form like higher level allocators, and then you have policies to control the creation of those higher level allocators. So the most simple allocator is an identity allocator. It has one element, and it is either allocated or not. But at this point, the element does not actually have any address in memory. This is just purely a concept, and it is basically for the data layout. So let's go into the next one. There is the pool allocator. A pool allocator can allocate from one of multiple allocators inside it. And you have the union allocator. So you can allocate from either one allocator or the other. So do two different types of allocators. You can compose these in all kinds of ways. So you see here we have a union allocator, which either allocates an identity element or a pool of elements. And then finally there is a segment allocator, which links together multiple pools of allocators, so that you can have really large allocations without using only one pool. Finally, here is where actually the object does get a fixed address, is in the global allocator data. So for things like head pointers and stuff, you need one fixed data for the entire pool. And that's what happens there. Okay. And then at the end, you put your entire allocator, your entire high-level object that you created in one object, and you allocate it like you see here. So this entire object is just that alloc type, and you put it wherever you want. You can also have this thing on the stack in its entirety. So in this case, I have a bitmap allocator that allocates these segments within the stack, but you could also move it to the heap. So in this case, the only thing that's on the stack would be the root and the head pointers, and then you allocate your segments on the heap. And the advantage of that will be that you do less heap allocations, and so you do less system calls in total. So you might have seen this multitype pool type, where you put all your allocator types. That is a bit of unicorn code. Basically what it does, it just figures out all of the types and sees what the best way to put them all together is to get the least amount of fragmentation possible. So some benchmarks. I compared the buddy method, so it powers off to allocation against this pool. And in this case, I'm using 24 and 40 byte objects, which is pretty normal for something like a point cloud, which has octree nodes and points itself, so 2 types. And in this case, well, I didn't actually benchmark the buddy allocator itself, because that would require more work. But you can expect about 20 to 25% fragmentation. And in this case, I could actually calculate my best and worst case fragmentation at compile time in my allocator. So best case fragmentation is about 2%, and worst case about 8%, which is pretty good, I'd say. So in conclusion, with the allocator, you can give hard real-time guarantees because of you have a fixed data structure, and you can you have a maximum level of allocators without any polymorphism. You reduce fragmentation, and it might be possible to get more performance out of it, but I haven't really looked further into it. And with the modularity, you may know about using top-level allocators that keep track of allocations and deallocations, so you can test for memory leaks. That is also something you can do in this structure. So closing remarks about metaprogramming. I think it is actually quite a new field, and we're just now starting to see kind of the implications it has on library design and optimization in general. So I think with more research into how to actually apply metaprogramming and apply it to things like interfaces or things like allocators and whatever have you, I think long strides in that can be actually made. All right. So if you want to have a look at the allocator implementation, it's right there. You can reach me at any of these places, and I will probably give a full-length version of this talk at EMBO, so you can check that out too. Thank you.
Thank you very much. And we are still, do we have questions?
Thanks for your talk. Referring to your so-called unicorn code, so this basically takes a variadic pack of types,
yes,
or of allocator
of allocator types.
Of allocator types, and it gives me one like merged allocator type back.
Yeah, so basically in the example of the 24 bytes and the 40 bytes object, it would create two identity allocators and then two pool allocators from that. And then try to figure out the best sizes to combine them together so that they overlap in the best way. That's right.
What method do you use to figure out which is the best size of the allocator?
Right, that is kind of an open problem. As I found out, it's really hard to find the best solution. Right now, I just use a greedy search. So basically, I first increment one size of the pool and then the other until they are they're bigger than the other, and then I just see whichever has the best fragmentation. I know for a fact that it's not perfect because, there's many variables to consider, but it works for now. But yeah, that will be something that has to be researched further.
Also, it is probably pretty easily exchangeable, right?
Yeah.
Yeah. Okay.
Yeah.
Thanks.
Hi, Giel. That calculation where you calculate the optimum overall allocator, is it done in metaprogramming?
Yes, it is entirely in metaprogramming.
Could it be done in ConstExpr?
Maybe.
I was wondering what the future is in this kind of programming, in the balance between metaprogramming and ConstExpr calculations.
Well, okay, so the problem if you do it in ConstExpr is that you cannot test for the size of the types itself. So you have to make assumptions about what the final size of your allocator type will be. So, and that can be implementation specific, I think. So if you do it in type-based metaprogramming itself, you don't actually have that problem because you can always say type or size of this type.
Okay. Another question: you say there is real-time guarantee about the complexity of the allocate and deallocate calls.
Yes.
How can that guarantee be used? Do you export it in some way? Can you make further calculations with it, or do an assert that it's below a certain level? Or
you could actually make a combination algorithm that has a maximum. You give it a maximum allocation time, and then it will create a structure that is no more levels than whatever that time is, so that you always stay under that time bound.
But you stay under a certain level of complexity. There's no direct relation with runtime. It's
No, like you could actually calculate the runtime it can have at most at compile time, and then use that to, in the combination algorithm, to create an allocator that has at most some runtime.
Okay, thanks.
Thank you. I see we are having another question, and if it's not a problem, it would be the last question for this talk, because we have only 15 minutes to prepare for another presentation.
Building on what Wouter asked, I would imagine that because you calculate everything at compile time, there are no indirect calls in this allocator that some kind of static analysis of the assembler could not reason about.
Yes.
So that would be a way with external tooling to be able to enforce, because before optimization, it's kind of hard to reason about it, but yeah.
Yeah. Yeah, exactly. That's yeah.
So if I understood it correctly, you for the analysis only take into account the types of objects that I want to allocate.
Yes.
This of course does not help you with analyzing what the maximum size of the pool is supposed to be, right? Because for that you would also need to know like how many of those objects you're actually going to allocate.
Well, you do that in the combination algorithm. So you could, for instance, make a combination algorithm that has a policy for how many objects there need to be at minimum for a specific type. So Yeah, that's another. You would need to create a special combination algorithm for it, and there's a bunch of combinations algorithms you would be able to write, and I'm not entirely sure how to write them. So yeah, it's kind of hard to do, but
you're considering it, or
I am considering it.
Okay,
yeah.
sounds great. Thank you.
Okay, thank you.
Okay.